Okay, talk to you today about photochemical vapor generation, and I'm sure you've had lots of lectures and you've read about this and you're familiar with it to some degree. I'd like to take a little bit of a different angle here and try to give you a comprehensive picture of photochemical vapor generation. And so I've entitled this a tool supporting ultratrace analysis. And what I would like to do is take you through the entire process. What is it and how do we implement it in the laboratory? Where are we going with it? What has been accomplished? What remains to be done? And what are the mechanisms, perhaps, that can account for photochemical vapor generation? So let me just get a little pointer here. And I'll start with an outline of what I would like to present. And this will certainly be a general introduction to vapor generation techniques themselves. Move on to what exactly is photochemical vapor generation? What are its capabilities? What is the scope of photochemical vapor generation? And I think this list of elements that you see here to the right-hand side pretty much summarizes that scope already. The ones that are in white are all the elements for which there are publications on the development of photochemical vapor generation techniques that have actually had applications with them. So they've actually been applied in an analytical situation to show that they are feasible for real-world samples. The second group of elements shows a list of those that have been published as investigated for their photochemical vapor generation capability, but the yields of the product have been relatively low. And so at this time, they don't look like a viable means of doing actual analytical work. Now, of course, that doesn't mean that we're stuck. I think just further development in these areas will eventually improve those yields. So as I mentioned already, I'll talk about the practical realization of photochemical vapor generation in the laboratory. I'll give you an illustration of the impact of different experimental variables that you would have to look at in optimizing your generation yield. Briefly describe, well, maybe not briefly, we'll go into some mechanisms of photochemical vapor generation as we see them at this current stage of development. Introduce you to the use of catalysts and sensitizers in this area, because not all yields, especially for an element like chlorine and fluorine, are very high in the usual way of applying photochemical vapor generation, and they rely on the use of sensitizers, which I'll discuss. And finally, just for the balance, the pros and the cons, we'll talk about some interferences. It certainly is not an interference-free technique, and we'll end up with some conclusions and perspectives. So to start with, let me get rid of that. To start with, what's a definition in general of vapor generation? And you can read this. It's basically just the conversion of non-volatile or semi-volatile species that you're interested in to volatile species, which can be manipulated to improve the performance of an analytical technique. So we're going from non-volatile to volatile. And of course, we deal with solid and liquid samples. In the case of a solid, sometimes it's possible to generate a volatile species just by thermally treating it. You could slowly heat it and drive out volatile species. But we've done that in particular for volatile butyl tin species, and we can selectively determine them. More often than not, though, a solid with usual atomic spectroscopy instrumentation is converted to a liquid, because a bulk sample becomes more representative when a large mass of it is converted to a homogeneous sample, such as a liquid. And once in a liquid form, it is chemically or photochemically derivatized, and that results in a volatile species, which through separation of that species from the liquid in a gas-liquid separation process allows for transport to the source or the detector. Why do you do vapor generation? I think you've seen this probably in every lecture on vapor generation. It's because primarily we're interested in improving the ability to get more of the analyte into the atomic spectroscopy source than we can with conventional liquid sample introduction. And I'll highlight that as a specific example in a moment. So enhanced introduction efficiency. And when you think about this vapor generation process, you realize the sample itself is not introduced into the source, but rather there's a matrix separation, and it's the analyte that goes into the source. The matrix in the remaining liquid phase goes down the drain in the waste. You can have some high selectivity for these processes, obviously reduced spectral interferences, sometimes reduced matrix interferences, of course, because of this matrix separation. And you will obviously see anywhere from 10 to 50-fold enhancements in sensitivity and limits of detection. I've grayed out a number of other advantages as to why we want to do vapor generation here. I guess we could always, here for academics, it remains an exciting field of research. So sample introduction for atomic spectroscopy. Vapor generation inherently provides that matrix separation and increased flux of analyte. This results in enhanced detection limits and improves the spectroscopic selectivity of modern instrumentation, and by that I mean also reduces some interferences. By way of comparison, we can see that pneumatic nebulization that's used for flames and ICPs typically has a sample introduction efficiency in the range of 2 to 5%, unless something heroic is done, in which case if you are using low flow, high efficiency nebulizers, or something called a torch integrated sample introduction system, you can up those efficiencies to approach vapor generation at 100%, but that's only at sample flow rates of less than 100 microliters per minute. You could resort to electrothermal vaporization or laser ablation, in which case sample introduction efficiency are 20 to 80%, but this is slow and it comes with introducing a sample itself and a lot of matrix effects. This slide was courtesy of John Olesic. He has been probably preeminent in looking at analyte transport efficiencies in ICPs. And if we look at the transport efficiency, or the percentage of analyte that actually reaches the plasma as a function of the sample uptake rate or the delivery from the nebulizer, we find it's only at very low flow rates in the order of 20 microliters per minute or less, where you can achieve efficiencies on the order of 60 to 70%. As we move towards higher flow rate delivery to the nebulizers, our conventional concentric nebulizers operating at a milliliter per minute, you see this drops down to the order of 2 to 5%. And that's because the droplet density that's produced here is so great that you have a lot of droplet coalescence, and most of the sample goes down the drain. So these are high efficiency nebulizers. If we look at a vapor generation, if we had the ideal manifold for this and we could generate 100% efficiency, which we sometimes do, and we can do it at flow rates up to 5 milliliters per minute or more, we can find that there's actually a 500-fold enhancement in the potential flux of analyte atoms per second or per minute that would reach the detector as compared to what can be achieved even under the best conditions for high efficiency nebulization. So this results in enhanced detection limits and sensitivity. There's a number of modes of vapor generation, and they've been around really since about 1967, starting with the formation of cold vapor mercury, of course, and moving towards a whole plethora of different ways of forming vapors. You can see there's the volatile chelate formation, chemical vapor generation, you know this with tetrahydroborate, electrochemical vapor generation, sonochemical, photochemical, plasma-assisted vapor generation, and thermochemical vapor generation. I'm going to talk today, of course, about photochemical vapor generation. Our work in this area started after we became aware of this paper here in 2000 in the Journal of the Electrochemical Society. A couple of Japanese workers had shown that in the presence of titanium dioxide, which is a well-known photocatalyst, that an aqueous slurry of this material, this catalyst, could be used in a solution in the presence of formic acid and selenium in the form of selenate to generate volatile selenium species, hydrogen selenide. Well, this got our attention because, of course, hydrogen selenide is what we like to produce when we use sodium tetrahydroborate to do vapor generation of selenium. But what was more interesting here is that it was the selenate that was generating the hydrogen selenide. Normally with tetrahydroborate, it's only the selenite that efficiently generates the hydrogen selenide. So this was a way to get access to other forms of selenium and potentially other elements. So we started to investigate this back in 2003. And our first setup is basically schematized as shown here. The sample was mixed with what I'll call a low molecular weight organic acid. In this case, formic acid was our first choice, going back to this paper here. But we could use acetic acid and even propionic acid. So the sample is mixed with this acid in an aqueous solution, and it's exposed to a UV field. And the UV radiation here was a simple alignment pen lamp. It's a 3-watt light source. And what do you see? Here's that little light source here, and it was wound with a little quartz coil through which we could pass the sample. So the sample gets irradiated, passing around this UV light source. The liquid is then transported to a gas-liquid separator for phase separation, and the volatile products passed to the detector, which could be basically anything: a flame, an ICP, a quartz tube, heated quartz tube, etc. So we could detect the vapor that was formed. This little lamp here is a non-ozone generating lamp, so it means it was limited to wavelengths below 254 nanometers. Currently, what's a present status or scope of photochemical vapor generation? Based on a periodic table here, we had that set of elements I had on one of the first slides. We have a demonstrated yield of all these blue elements. So we're getting to fill in a large portion of the periodic table, which is of analytical interest, especially for trace element analysis. The ones in yellow are expected, what I'll call expected to yield photochemical vapor generation in good enough quantities to give us analytical methodology. And those ones that I've highlighted before have so far low yields, a couple of these noble metals, and I know that Dario Borges has investigated these, and we haven't looked at fluoride. So hopefully we'll be able to increase the yields of these materials. We see some signal from them, but the yield is relatively low at this time. They have been used, actually. I think Daniel did use this in a publication in JAZ to show some results for the analysis of materials. Going back to advantages of vapor generation, specifically, what are the advantages of photochemical vapor generation? It's a green chemistry, and by green, I mean we don't use any toxic or unstable reagents. We're using typically formic and acetic acids, and these are present in the environment. They're decomposition products of organic detritus. It eliminates the need for fresh chemical reductant, in this case, sodium tetrabihydroborate, as compared to chemical vapor generation. It simplifies flow injection manifolds. We only need one line. We don't need to merge two, a borohydrate line and a sample line. There's a less violent reduction process. We're not doing hydrolysis of sodium tetrahydroborate. We're simply generating volatile material by photolysis. This reduced hydrogen is more compatible with plasma sources. You won't extinguish, especially low-power plasma sources. We did find reduced interferences from some concomitant element species, particularly transition metals. There's a high efficiency for product generation, giving us enhanced limits of detection, some direct speciation scenarios, and as you've seen from that periodic table, obviously some broad application areas. The disadvantage is there are now interferences from oxidants, and I'll give you an example of that. I'm not going to take you through any applied techniques to show you results, with the exception of this one, which perhaps is kind of an ideal situation. This is a comparison of the limits of detection achieved through conventional pneumatic nebulization and when photochemical vapor generation is coupled to an ICP-MS. This was the determination, simultaneous determination of three elements, nickel, selenium, and iron, in a digested tissue of lobster hepatopancreas, I think it was. What I want to highlight here is the enhancement factor in the ratio of the detection limits to these two techniques, anywhere from 30 to 150-fold. So clearly, it does offer significant analytical advantages. Now, there's two things that go into giving this big factor here. One is that pneumatic nebulization was limited to a flux or a flow rate of 1 milliliter per minute with a conventional nebulizer spray chamber. With PVG, the sample flow rate was 4.5 mils per minute. So about a 5-fold increase can be attributed to the enhancement factor here. The remainder is the improvement in the sample introduction efficiency from 2% in a conventional nebulizer spray chamber to upwards of, under compromised conditions, upwards of 30% for selenium in this particular situation. I'd like to backtrack now and give you some more fundamental information about photochemical reactions. And if you look at the photochemical literature, there's basically two general laws that must be obeyed. And the first is that in order to have a photochemical reaction, photons must be absorbed by a molecule for the reaction to take place. And this usually results in an excited state, which has different physical and chemical properties than the ground state of the molecule. And often it becomes more acidic, it becomes more reactive, etc. And the second law is that for each photon absorbed, only one molecule is activated for subsequent reaction. So what does this mean to us as experimentalists? It means that we require an appropriate chromophore, something that's going to possess an absorption structure. The analyte is going to possess an absorption structure that overlaps with an excitation feature from the UV visible source that we are irradiating it with. The second is that the rate of excitation, and therefore presumably the rate of the desired reaction and the rate of generation of the final material we're trying to measure, is proportional to the absorbed photon flux. So we can write a few equations for those of you who like a little bit of math. And then the rate of absorption of light in photons per second is given by something like a Beer's law. That's the incident intensity, the cross-section for the photoreaction, the number of species in the path, and that's the length for absorption. So the rate of the reaction is going to be given by K. And that's just this multiplied by something called the quantum efficiency. And the quantum efficiency of a reaction is the ratio of the number of product species formed to the number of photons absorbed. And that's everywhere in photochemistry. You'll always see people talking about the quantum efficiency. Obviously, the maximum is 1, and most frequently it's much less than 1 because of side reactions, etc. So we can put these relationships together by expanding this equation here. And I'm just doing this for fun because I just thought about it last week and thought this will be interesting to put this down. So the spectrochemical response R, this is the signal you're looking for, is given by this equation here. And obviously, through that first equation that was given back here, this one here, we see that the rate of generation of the species is given by this times the transmission efficiency of any conduits through which you're pumping the sample. Samples are pumped around the source, as I mentioned in one of the first slides, either in quartz lines or typically in PFA or PTFE lines. And they have a certain transmission efficiency for the spectrum that's of interest. And not all of them are good, of course. So the source radiation is going to be modified by this transmission efficiency to give a reduced photon flux. And then the efficiency of the reaction, of course, is going to be given by its intrinsic rate, which is that sigma, and the lamp irradiance, which is I naught, the transport tubing efficiency, the sample medium, and I'll come to that, whether we've got any catalysts or not, the flow rate of the sample, the efficiency of the gas-liquid separation process, the efficiency of the transport of the volatile species to the detector, and the stability of the species being gas-liquid separated or transported. So let's look at a typical laboratory arrangement. Very similar to the first slide I presented. We now in our laboratory work predominantly with what is called a flow-through reactor. This is a lamp in which the sample solution is directly exposed to the actual plasma discharge, the low pressure mercury discharge within the lamp, as opposed to transporting the sample in a coil around the outside of the lamp, in which case the UV radiation has to penetrate the walls of the lamp, penetrate the material of the coil and then be absorbed by the sample. Here the sample is right inside the actual plasma discharge. A couple of advantages of that. It's getting irradiated in a 360-degree geometry. It's being irradiated within the discharge, meaning it has the full irradiation from all wavelengths in the plasma, in particular, not just the 254 nanometer radiation that's typical of low pressure mercury discharge lamps, but also the deep ultraviolet or vacuum ultraviolet region down at 185 nanometers. So following irradiation, the samples passed, as I mentioned, to the conventional gas liquid separator. And in a flow of argon, it's transported either directly to an ICP, or if you're really lucky and you've got a dual inlet spray chamber, you can pass it to a spray chamber, which is also fed with a nebulizer, and you can do a lot of tricks here in terms of studying the vapor generation efficiency. So what do we have when we look at this equation again? We can link the response to the flow, which is just the rate at which we pump the sample through the system. We can link it to the fundamental parameters here, the intensity of the lamp, the wavelength, the transmission efficiency of the conduit in which the sample is passing around or through the lamp, the fundamental parameters, the concentration of the element in solution, etc., the gas liquid separation efficiency, the transport efficiency, and the stability. Looking at the variety of photoreactors, this particular lamp here is, of course, shown schematically, not shown in real life here. This is the discharge contained in the lamp, and the sample actually comes in here. It goes in through the lamp, so it's actually in that discharge, does a number of multiple passes, and then comes out to the gas liquid separator. This was the first one I showed you, a 3-watt discharge. Sample is pumped external to the lamp in a quartz tubing. This is a simple, inexpensive, works very well, germicidal lamp. It's about a ½ meter long, typically 15 watts. And here you see the lamp is wrapped externally with PFA tubing. So we pump the sample in, the irradiated sample comes out and goes to a gas liquid separator. We've also used light emitting diodes, and these are available now with more reasonable cost. They're still very expensive. They can cost a couple of $100 for each diode, but they're very small, 0.3 milliwatts, and they're available in the deep UV region. So you can buy them at 250 nanometers, 240 nanometers, but not much below that. Here's a lamp. This lamp here, placed inside a cyclonic spray chamber. You can introduce a sample via a conventional nebulizer and do normal sample pneumatic nebulization sample introduction, or you could augment that with some UV processes within the chamber. Here we just have a larger format version of this lamp. It's called a grid lamp. And over here, I'll get back to you towards the end of the slide, end of the lecture. This is a laser-driven light source, a $10,000 system, but it allows you to have complete selection of whatever wavelength you want, all the way from 200 to 800 nanometers. I'll come back to that in a moment. The emission spectra that comes out of these lamps, and so I mentioned to you the first law of photochemistry is that you must have a chromophore in the solution that will absorb one of these, some emission from the lamp, and therefore, of course, you have to have the emission from the lamp should be either completely, let's say, continuous over the full spectrum of interest, or if it is discontinuous, such as the line spectra from a mercury discharge source, you must have lines that overlap somewhere with the chromophore in your sample. So here we have the spectra of some typical light-emitting diodes. They have a full width half maximum of about 10 nanometers. And here you see one at 245 and another at 260 nanometers. This is the spectrum from a conventional fluorescent light in your laboratory. And you can see its line spectra. It looks continuous, of course, because these lines impact on the phosphor coating of the lamp, and they give you a continuum in the visible, but absent is, of course, completely anything below the UVB region. So we don't have any 254 nanometer radiation coming out. So these lamps, they actually may prove useful, and I'll give you an indication of that later for some photochemistry, but certainly not now. We're primarily interested in the 254 nanometer radiation and 185 nanometer radiation that comes out of these lamps. This is a typical spectrum from a germicidal lamp. This is the spectrum seen by the sample flowing through the 19-watt flow-through reactor. We can get the 175 nanometer. We can also get this spectrum in a lamp that is an ozone-generating lamp, because mercury discharge lamps can also be used as ozone generators. And under that situation, you do have the 185 nanometer line. It's just that they're not that practical in the laboratory because you need venting. This is the spectrum from that laser-driven light source I talked about a moment ago. So all the way from 200 to 800 nanometers, you have pretty much a continuum. So it's not structured. And for that reason, it may offer significant advantages at a high cost for future photochemical work. I have mentioned previously the epsilon lambda, which is the transmission efficiency of the conduits that you are using to guide the sample through or around the reactor. And in the case of PTFE tubing, even though it's thin-walled, the actual transmission efficiency of this material is getting low in the 254 nanometer region, no more than about 35%. And by the time you get to 185, it doesn't transmit at all. Even standard quartz, 2 millimeter thickness, natural quartz, has about a 50% efficiency in the 185 nanometer region. And that's why that flow-through lamp is constructed with synthetic quartz or suprasil. And here you see very high transmission efficiency for the UV into the sample through the suprasil line, still giving about 85% transmission efficiency. So let's look at some of the experimental optimizations in the practical utilization of photochemical vapor generation. It's obviously a dynamic system. It's a flowing system. And in a flowing system, of course, it is then the irradiation time of the sample which determines the total flux of photons that will be absorbed and presumably determines the total reaction yield that you will get. And if you're looking for high yield, of course, that means you will get a high response. And the irradiation time will be fixed in a flowing system by the volume that is being irradiated of that system divided by the flow rate. So ideally, we could have lengthy irradiation times if we had a high irradiated volume and a relatively low flow rate. But if the volume was high enough, we could even have a relatively high flow rate. So you can play with this parameter. Because of the limited irradiation volumes that we have in these relatively small lamps, advantage can be taken of what we call stopped flow irradiation. It's a convenient means of evaluating the impact of irradiation time on the yield without perturbing the performance of the gas-liquid separator. And I'll show you what I mean by that in a couple of moments. The net response that you get in your R factor, your yield, is a result of the rate of formation of the volatile material versus its rate of decomposition in the irradiation field. So if you're pumping for a very long residence time, or you have an unstable volatile product, the longer that it remains in the UV irradiation field means that not only can we form more product, but that unfortunately the product may undergo UV decomposition. So there is a balance to be achieved. Here's an example of what happens in the case of iron and iron 2 and 3. This is using an old germicidal lamp. So we had a fairly large volume of wound PTFE tubing on the outside of the lamp. But as we increase the irradiation time, we find that ultimately we reach a plateau where maximum efficiency is generated. So we need, in this experiment, something like 300 seconds for irradiation. We had a 5 milliliter internal volume of that tubing wrapped around the lamp, exposed to the UV. And this provided us with a flow rate, a convenient flow rate of 1 milliliter per minute. And that would give us a 300-second irradiation time. This, of course, meaning that beyond 300 seconds, even 450, there's no change in the signal, is that we seem to have a UV stable product. Here's a case where recent investigations into the generation of a volatile osmium species has shown that we do not have a stable volatile product once it's formed. And here's a case where we've done stop flow irradiation. We fixed the flow rate at 2 milliliters per minute, introduced it into the lamp for various periods of time, found out that the optimum irradiation time here was 21 seconds in the UV flow-through lamp. So we have an intense irradiation field here. Anything longer than a UV irradiation time of 21 seconds started to result in a decrease, actually, in the yield or in the signal at the detector. And therefore, this is indicative of a UV unstable product. Now, the efficiency of the gas-liquid separator is something to be concerned about because we've concluded this is a UV unstable product because we kept the flow rate of sample to the gas-liquid separator constant at 2 milliliters per minute. We did not increase it or decrease it below that flow rate. So we knew the efficiency of the gas-liquid separator was fixed at that fixed flow rate, and any change in the signal had to be due to the increased irradiation time photochemically decomposing the product. But there are some cases where you do need to be concerned with the efficiency of the gas-liquid separator because its performance is going to be analyte dependent. It will be dependent on the properties of the analyte, or rather the volatile product formed by the analyte, its hydrophobicity, its vapor pressure, its solubility. Something like mercury, we know, is highly hydrophobic. It's very stable. It has a high vapor pressure. It can be quickly released from the condensed phase of the liquid. But the performance can also be dependent on the physical property of the gas-liquid separator, and that is the flow rate going through it. The response we get at the detector is going to be the overall convolution of the impact of the irradiation time in the source and the phase separation efficiency in the gas-liquid separator. And both parameters may require optimization. Clearly, we optimize the case for osmium, and it's convenient to use that stop flow irradiation as a convenient method of also optimizing the efficiency of the gas-liquid separator. Ideally, the response should be directly proportional to the flow rate. The greater the flow rate into the detector, the greater the response, obviously. So if you can increase F without compromising the performance of the generator or the gas-liquid separator, and the transport efficiency is constant, the signal will vary directly as the flow rate. Here's a compilation, some schematic and actual photos of various gas-liquid separators. Some of them rely on what I'll call a quiescent mode, where in fact the solution is coming in the sidearm here at a flow rate such that it flows down a quartz tube, and it's in the form of a thin film. And as the thin film flows down, its thickness is very low, and the volatile product can diffuse out of that film and then be transported in a countercurrent of argon to the detector. Here's an example where we may have a forced operation, a mechanical forced operation of the gas-liquid separator. The solution from the photoreactor is delivered to the top of a frit through which a stream of gas of argon is forced, and that creates a lot of bubbling and enhances the gas-liquid separation efficiency mechanically, and that drives it to the source. And there's an example of a gas-liquid separator fitted with a frit. Here's an example. This is a picture of this gas-liquid separator where it just comes in the side, runs down the film here. Okay, well, the experiments we did were relying on this particular generator. And the results that we got, again, for the osmium efficiency, if we use that 21-second optimum irradiation time and then vary the flow rate to the gas-liquid separator, we can find that initially it looks like the response is in fact proportional to the flow rate. So that's to all expectations. But after this, coincidentally, this initial 21-second irradiation time, which in the photochemical reactor did correspond to 2 mils per minute, when we go beyond that for delivering the photolyzed sample to the gas-liquid separator, we find the efficiency of the gas-liquid separator decreases. And in fact, this decrease looks a lot like photochemical decomposition, but in fact it's not, because we stop the photochemical activity here at 21 seconds and then rapidly delivered this to the gas liquid separator at different flow rates. So this is an example of the efficiency of the gas liquid separator falling at flow rates higher than 2 milliliters per minute. Some more experimental optimization. The generation efficiency is highly dependent on the composition of the irradiated medium in which the analyte is placed. Chemically stable products have been identified in the form of hydrides or alkylated products of the metals in formic acid and acetic acid, carbonyls of metals in formic acid, and alkylated halogens in acetic acid. Sometimes the pH of the generation medium also has an effect on the response. And an example of the response of iron again in 3 different acids: formic acid, acetic acid, propionic acid. Note the absence of response in these 2 acids. The only time we see a signal from iron is when we photochemically generate it in acetic acid. This was in a germicidal lamp. I don't know what the performance would be in the flow-through lamp. It may change. Here's a case for iron where there's a pH effect, and it's fairly pronounced in the range of 2 to 3. What is happening here, we can't be sure. It could be that there's an optimum for generation of a formate complex of iron here. It could be that it is the degree of dissociation of the formic acid that's causing a reaction rate dependence here, because the generation of radicals, as I'll show later, that occurs in formic acid is dependent on the formate rather than the hydrogen formate form of formic acid. Anyways, you need to investigate all of those kinds of experimental parameters to optimize your signal. The composition of the medium, the irradiation time, and possibly even the performance of your gas liquid separator. Shown here is a summary of the dominant products of photochemical reactions for a wide variety of analytes that have been examined in the literature, and whether or not it's been done in formic, acetic, or propionic acid. And here's a summary of the photochemical yield. And they're all quite high, as you can see. Those cases where there's a question mark means that the product has not been unequivocally identified using such techniques as GCMS. They are inferred in many cases based on similar chemistry to the identification of products in similar areas of the periodic table. So here we have a case in point. Let's look at this. Going from formic to acetic to propionic acid, we find that we transform the product from arsine to dimethyl, or rather trimethyl arsine to triethyl arsine. Similarly for bromine, we get no product in formic acid. HBr, of course, doesn't have a significant vapor pressure, and it remains dissociated in the liquid phase. But we do find methyl bromide and ethyl bromide generated in acetic and propionic acid. For iron, in all 3 acids, you form only the carbonyl, the same as molybdenum, nickel, and tungsten, and probably rhenium. It's all the carbonyl. That's all that's formed. So there's a couple of points here. We form cold vapor in the case of mercury. We form hydrides for those typical hydride forming elements. We form alkylated species for those typical hydride forming elements and the halogens. And we form carbonyls for these transition metals. But the highlights is that we have a high yield, that halides, metals, and semi-metals can all be subjected to photochemical vapor generation. And I think there's evidence that there's a radical mechanism here that gives rise to these products. And if we look at that case of arsenic, in formic acid, acetic acid, and propionic acid, look at this side arm here. We generate arsine, trimethyl arsine, and triethyl arsine. So probably radical processes. Well, what's going on in our typical experimental setup? We have the sample mixed with a carboxylic acid here. So it could be in the form of a simple aqueous, or it could be a ligated complex, or some other complex in solution. We pump it through the lamp, separate it through the gas liquid separator. And at this point, we can experimentally look at the products, in some cases with GCMS. And we see those products that were in that previous table. We have alkylated species, hydrides, cold vapor, more hydrides, and carbonylated products. So the question is, what's happening in this lamp to produce these products? And we believe that there's radical-mediated reactions. And the radicals that are produced in this lamp are things such as equated electrons, radical species such as ethyl radicals, methyl radicals, carbonylated species, the carboxyl anion radical, hydrogen atoms or nascent hydrogen atoms, which is the H radical, etc. So I'd like to take you through some of the mechanisms that we believe responsible for these reactions. Support for those presumptions are that there's a lot of vacuum UV and near UV radiation chemistry that's been extensively investigated for the generation of reaction intermediates over the last 50 years, but particularly over the last 20 years in organometallic synthesis. We have transition metal species being widely exploited in the photochemistry for preparation of organo and organometallic compounds, which serve as redox active catalysts and triplet sensitizers. We know that there's ligand to metal, metal to ligand, ligand to ligand, and charge transfer to solvent redox reactions occurring during UV irradiation. And I'm going to make reference to some of these, so I'm going to be using these acronyms. And there's a vast amount of literature, especially from the 1950s to the 1970s, and some still going on today, where VUV, UV, pulse radiolysis, laser flash, and steady-state photolysis of aqueous solutions containing inorganic salts and various organic compounds have been widely studied. And in all cases, they're coming up with proposals for these reactions being mediated by sets of radicals such as those identified here. So here's a typical example way back before most of you were born, probably all of you. 1974, production of hydrated electrons from the irradiation of formate ions. Here we know that in a simple water solution, we can get UV homolysis of water to yield H and OH radicals. And this gives rise to a lot of the oxidation capability of water. But the moment we add formate as a salt or as formic acid into this water medium, a new set of photolytic products are formed, including these radicals, HCO2 dot, free electron, the carboxyl radical anion, and moreover, some chemistry. Not photochemistry, but chemistry can be involved with these radicals, giving rise to species such as carbon dioxide, stable molecules, carbon monoxide, hydrogen, more capable radicals such as the carboxyl metal radical. And what we end up doing is reacting this initial OH radical, which is responsible for oxidative products of water during photolysis, to create carboxyl radical anion, which is responsible for reducing properties. So this kind of modeling situation here, or actually experimental evidence, accounts for the gaseous species we see coming out of the gas-liquid separator: hydrogen, carbon dioxide, carbon monoxide in acetic acid, as well as these products and methane, and even acetylene and ethylene that come out during the photolysis of acetic acid. So we go from a photoinduced oxidizing medium in water to a photoinduced reducing medium in the presence of formate, actually formate, acetic acid, or propionic acid. So we saw from the homolysis of water gives OH, but the moment that a carboxylic acid is present, we can generate these radicals. Foremost amongst, we can get this carboxylate anion radical. So we've gone from a powerful oxidizing solution to a powerful reducing solution. So not only do we have the CO2 dot minus, we have R dot, and we have the free electron. And these have very high reduction potentials. In fact, the electron, of course, is at the top of the scale, E0 versus the standard hydrogen electrode. And you can see the magnitude of H dot and CO2 dot minus. Very strong reducing radicals. So if we put these into perspective and we plot these potentials up here for these reducing radicals on the same scale as we find for these half reactions or electrochemical series for all the elements that we've so far looked at, they are all above. And that means they're capable of reducing all of these species. I've also included simple ethyl alcohol. It generates a reducing radical, which is very capable of undertaking reduction of mercury. And there's a publication on this by Howe that I'll draw to your attention a little later. Also on this scale is the semiconductor anatase, which is TiO2, and there's the valence band and the conduction band for electrons, and I'll come back to this later. Also, these conduction bands are very highly reducing. So let's look at some of the processes. So let's look at general metal ion reduction in a solution. Obviously, if we have free electrons in solution, these will readily reduce the metal ions of interest to their zero valence state. In addition, this carboxyl anion radical certainly has the reduction potential to also reduce metal ions to their zero valence state and generate carbon dioxide. Now, we can have dismutation reactions at this point where two lower reduced metal ions will get together, forming an M0. But I don't think this is too important right now compared with the photochemistry that's going on. So when we apply this to iron, for example, iron 3 or 2 in a photolyzed solution, undergoing reduction reactions with all of these potential radicals, we ultimately end up with iron 0. So this could be a nascent free iron atom. We also know that carbon monoxide is present during the photolysis of formic acid. It's freely available in the solution, so it can come along and abstract this iron 0 to form, ultimately, the stable iron pentacarbonyl. In addition, the free electron can react with carbon monoxide to produce a CO dot radical, which in itself does not preclude the possibility of the CO dot radical reacting directly with M+, giving a MCO product here. And then CO can further react with MCO, giving MCO2, MCO3, etc. I really do not know what the stages of the ultimate carbonylation of the final product are here, since we're starting with a nascent metal atom. Does it go through individual CO steps or just what does happen there? I'm not sure. But certainly dismutation and nucleation can occur, as I showed previously. Here's an example of a sequence of nucleation dismutation forming ultimately what we'll call a nanoparticle. So this will be a solid nanoparticle, and it doesn't take many atoms to form a nanoparticle, maybe roughly 20. And at this point in time, we have now a bulk metal species in solution, which can then undergo carbonylation. And whether or not that has to happen to generate this product up here, or it can go through nucleation steps directly from M0 with successive addition of CO, I don't know. I couldn't find anything in the literature to suggest otherwise. And you know, with the case of nickel, the Monde process is industrially used, but I didn't come across any sequential reaction to show how the Monde process works, whether, it starts with, of course, solid nickel and a presence of a high pressure of carbon monoxide generating nickel carbonyl. But is it sequential reaction, one at a time, or does carbon monoxide cover the surface and lift off as the stable tetra nickel carbonyl? I don't know. The production of the carbonyls for molybdenum, tungsten, iron, nickel, and cobalt, we find that there's low or no yield in acetic acid. So the question is, why is that? And it may be the result of the rapid uptake of any free carbon monoxide in the solution caused by the co-produced methyl radicals. These things can get together and produce a variety of products here, which of course are no longer available for carbonylating a reduced iron or nickel or cobalt. This, of course, is just acetic acid, so it could start the process over again. But depending on the kinetics of this reaction versus the kinetics of this kind of reaction, we may find that is the reason why there's no yield in acetic acid. Transition metals such as lead, tin, and cadmium. We haven't identified these products, but we surmise that they may be hydrides in the form of like SNH2, CDH2, which is relatively unstable, of course. in the case of cadmium, they may form in formic acid, and maybe the methylated species may form in the case of acetic acid. All ions are easily shown to be reducible by formate and acetate media due to these reactions, and therefore we can have products such as this readily formed. And in fact, a radiation experiment here was shown to actually be useful for the removal of lead in aqueous solutions by radiolysis, which means that this reaction was happening here, and that's a study in 2006. PVG of selenium, I show the electrochemical series for selenium here because we can see theoretically with the aqueous electron and the H dot and the CO2 minus radical anion sitting up here, more than capable of thermodynamically reducing both selenium-4 and selenium-6 to the 0 and even on to the -2 state. Now, the most commonly studied species of selenium are selenium-4 and 6. And therefore, in the case of selenium-4, we can speak about a homogeneous reduction by these radical species in solution, so it's a homogeneous reaction, undergoing sequential reduction of the selenite species, ultimately to selenium-0. And then along come the final coup de grace, I guess you could say, and H dot comes up here, or CH3 dot, forming what we have GC identified as selenium hydride and dimethyl selenide. Now, it's also possible that the selenium-0 does the reduction does not stop here, but goes to the -2 step. And if it does go to the this 2- species in solution, we know there's more than enough H+ in these aqueous solutions at pH 3 to simply have an ionic reaction here to generate selenium hydride. Now, when it comes to the case of selenium-6, we know that although thermodynamically it's capable of being reduced, kinetically this does not happen very quickly. In fact, there's no Faradaic current noted during voltammetric reduction of aqueous solutions of selenium-6. There's an inertness of selenium-6 towards the classical derivatization of selenium-6 using sodium tetrahydroborate in solution. We know experimentally that there's a very poor yield using PVG to try to generate selenium from selenium-6. And we have become aware that semiconductor catalysts enhance the kinetics of reduction of selenium-6. So that leaves us to believe that selenium-6, the fact that we're not getting much signal for standard PVG, is because it's kinetically slow and it requires a photocatalyst. Now, I mentioned TiO2 in that a few slides back. It is a standard photocatalyst. And in a photocatalyst, you can illuminate particles, nanoparticles of the photocatalyst with an appropriate wavelength that is suitable to cause charge separation within that photocatalyst. And that's called the band gap in the photocatalyst. And a specific UV energy is required. In this case, for anatase, it's 3.2 electron volts, corresponding to a 388 nanometer irradiation of light. So 388 nanometer radiation is absorbed, and that separates charges with electrons going into a conduction band and holes being transformed into a valence band. Now, in this situation, under continuous photolysis, sacrificial oxidation material, such as formate, can come along here and get these holes abstracted or react with the holes to create oxidation of formate to produce CO2 and water. Conversely, metal ions could come along here and be reduced by the conduction band electrons. The conduction band electrons have reduction potentials of approximately -0.2 volt, but they are pH dependent. There's been a significant study, fortunately for us, by a lady by the name of Rose Amel in Australia in the early part of the century. She did a lot of studies on the photocatalytic reduction of selenite and selenate using TiO2 as a photocatalyst. And using a number of techniques, she deduced that formic acid as well as selenium-4 and 6 are adsorbed onto the TiO2 surface in the first step of this reaction. And then secondly, the 4 and 6 are reduced by conduction band electrons to selenium 0 to produce a metal film. And then obviously at that point in time, we can have extraneous species such as carbon monoxide or H dot to come along and attack that film and result in the volatile selenium products. So here we are, the TiO2 surface reaction for selenate. We have production of conduction band electrons and valence band holes. What do we do with those electrons? We can have sequential reduction of the adsorbed selenate anion and eventually result in adsorbed selenium, which can be further reduced to selenium -2, react with H plus in solution to give you hydrogen selenide. But with the case of the holes, we have these sacrificial formate and acetate, which are oxidized to CO2, CO2 minus. So there's actually a benefit to having TiO2 in solution, not only for potentially for selenate, but from a more general perspective, you can see that it's possible to generate these reactive radicals in solution at wavelengths of 388 nanometers. So we would enhance production of these species at wavelengths less than 254 nanometers. And this is a whole area that needs to be investigated with photochemical vapor generation. Since these semiconductor materials are found so useful for selenium, a number of researchers, particularly those in China, Chichan Wang, started investigating very early the engineering of these particles with traces of other metals that would change the conduction band potentials of the generated electrons and result in a more electronegative electrons with greater capability for reducing species. And he found the kinetics of the reaction were improved a little bit when silver was adsorbed onto the species, onto the TiO2. This is called, in general, decorating the semiconductor species. And there's a whole field of interest in this area that you can go into in the literature. If we turn our attention to mercury, one of the most easily reduced species in solution, we find that in the case, even using ethyl alcohol, we can generate this reactive reducing radical here, has a potential of -0.9 volts, and that's enough to reduce mercury 2+ in solution. And in fact, Dan Howe published this paper in 2006 where he didn't have to add any formic or acetic acid to a sample of alcohol, but he was able to generate a mercury 0 from an irradiated solution quite readily. And that's because of the production of this radical here. But other than that, there's numerous photochemical reactions that mercury can take part in. And a lot of this can be drawn from the environmental literature of mercury because it does a lot of biogeochemical cycling. So you can have direct reduction of the most dominant form of mercury in solution here, Hg2+, to give you cold vapor. You can have dismutation reactions. You can have a ligand to metal charge transfer reduction if you have the form of carboxylic acid of mercury. That will generate mercury 0, as well as this radical here in a radical reaction. You can have something called a halogen atom abstraction during the reaction of something like methyl mercury chloride. The homolysis of this reaction will generate HgCl, splitting this bond here, and H3C radical. This can come along either from this product or from a reaction generated from acetic acid UV irradiation to react with this species here and abstract the chloride radical to produce the free mercury and this species. And this is important for us, and I'll emphasize that in some coming slides. In fact, starting here, what happens when we look at halogens? Halogens can be photochemically generated quite readily to form the volatile ethylated and methylated products. If we look at the photochemical literature of the halogens, and this goes back to the 1973 area with a fellow in Israel by the name of Jortner, his model has not changed much. Even in 2000, reinvestigated, the proposal was that aqueous halogens such as iodine has an absorption band head that is within the UV range of the sources that we're using, and it absorbs a photon and forms an excited state species, which undergoes what's called a charge transfer to solvent. And that's nothing more than the ejection of an electron into the water phase. And what it creates momentarily is something called a cage complex. It's an electron cage complex formed by the iodide radical and a free electron. These can ideally diffuse away from each other, in which case the iodide radical can react with another one to produce I2, or it can react with other radicals in solution, notably the ones produced from the photolysis of the carboxylic acids, and generate a product. So here we have the methyl and ethyl iodide. Similar reactions can be proposed for bromide and chloride. And in 1 to 5% acetic acid, we find that whether you're using iodide or iodate, bromide, bromate, chloride, chlorate, the same product is formed, the methyl halogen species. In formic acid, nothing happens, of course, because you would generate HX instead of RX, and that just dissociates. The reaction yield is highly dependent on which halogen you're looking at, because first rule of photochemistry, you have to have a chromophore absorbing the available energy from the lamp. And certainly we have lamp energy possibly at 226, some near 198, but we don't have anything at 178. 185 is the cutoff from our flow-through lamp, and certainly 254, maybe lower cutoff for the iodine. So what we have is an increasing difficulty in doing photochemical vapor generation reactions with the halogens. We find that with the iodine, as I mentioned, 95% yield, where am I now? Here we are. 95% yield with iodine and iodate using a 254 nanometer source. For bromine, we have a 95% yield of bromide and bromate using a 185 nanometer source. This is the flow-through lamp. But with chlorine, whether we use a flow-through lamp or not, because the maximum of the absorption bandhead is down at 178 nanometers, that may overlap a little bit with the 185 due to broadening of both this absorption structure and some slight broadening of the emission line from the lamp. There's very little overlap, and so the yield is not high. Nevertheless, we can take advantage of what I called the halogen atom abstraction reaction, pointed out earlier for mercury, when copper ion is present in the solution. And what happens here, we can go back to some photochemistry of transition metals, and we find that those that produce complexes of halogens in solution can partake in something called a ligand to metal charge transfer reaction. And that takes place in the UVB region, 347 nanometers. We no longer need 254. What's happening is the same kind of cage complex as we saw for the iodine, but in contrast, where the iodine was doing a charge transfer to solvent, it was kicking out an electron into the aqueous phase. What's happening here is this is a charge complex, a cage complex of iron chloride, where the chlorine has donated or transferred an atom to the predominantly metal orbital in this molecule and reduced the iron center from iron 3 to iron 2, leaving a chloride radical. Well, if we have a chloride radical around, it's not too long before a methyl radical in solution coming from the photolysis of acetic acid can abstract that before it recombines, and there we have our product. So this is called a radical halogen atom transfer instead of a charge transfer to solvent reaction. And with that, in the presence of as little as 5 parts per million of copper in the acetic acid solution, the reaction yield for chlorine increases about 70-fold. So we've gone from almost nothing here because of the very low overlap, very small overlap between the 185 nanometer radiation coming from the lamp and the 178 nanometer bandhead from aqueous chloride, to a significant generation efficiency, almost 80% in the presence of copper. Despite that fact, we still find that when we are looking for the halates, such as chlorate, we find different calibration curves for the different species of chlorine, different oxidation species of chlorine. And the reason for that is that the final reaction to form the methyl chloride obviously has to come from chlorine radical. In order to get to the chlorine radical from a chlorate species, the species itself has to undergo successive reduction stages like this. So bromate has to be converted to BrO2, to BrO minus, and finally to Br. Each of these species has maximum absorption coefficients at different wavelengths. And since the BrO3 reaction shown here is at the deepest UV wavelength, it's probably the rate limiting step. So kinetics is going to govern the rate of production of a signal from chlorate, for example. It's pretty fast for iodate, reasonable for bromate, and relatively slow for chlorate. So what we would propose in the case of bromate is that we can have an indirect reduction of bromate caused by the co-generated CO2 dot minus radical anion and the free electron in solution, more than enough reduction potential to take care of bromate at 1.44 eV, and that would eventually come down to bromide. So that's I'll call it an indirect homogeneous reaction. And we see that with, let me see, I'm going to go from bromate using this indirect reaction to the production of a signal from bromate with the presence of copper. And I'll come back to that slide here. We find that with the flow-through lamp, as I indicated earlier, we do produce a signal for bromide and some for bromate. But this is typically enhanced by the presence of ammonia, because in the charge transfer to solvent reaction, the cage is a bromide, a Br radical, and an electron. And if ammonia is present, ammonium chloride is present in the solution, the ammonium ion can react with the electron to prevent recombination with the bromide, bromide radical, and facilitate the reaction. But in this case here, we can also get a high generation efficiency in the presence of copper, and even in the case of cobalt. And we published a paper recently in this in JAZ with Richard and Daniel. So the flow-through lamp, that works very well. And even in the germicidal lamp at 254 nanometer radiation, we can get response from bromide, but none from bromate. So what's happening with copper in the presence of bromide? We can have that UV cage complex with the charge transfer to solvent, giving this, and then reaction with methyl, and this reaction to give us the product, which is what's happening in the flow-through lamp in the absence of copper. But when we add copper to the system, we can form the copper-bromide complex, which now can undergo a longer wavelength, higher yield ligand to metal charge transfer, forming this cage complex now, the generation of Br dot, and then again, abstraction with the methyl radical to generate the product. Or alternatively, we could form, obviously, this possible reaction here directly in solution of CuBr reacting with the methyl radical, halogen atom extraction, giving the product and reduced copper. So in this case here, what we believe is happening is the copper is acting as a substrate, a catalytic substrate, where H3C actually forms a complex and then splits off later. The copper plus that's formed here can be reoxidized quite readily in solution because of dissolved oxygen to regenerate copper 2 plus, which can then undergo this reaction again, or it can react with the methyl radical and some protons, again to generate copper 2 plus, regenerating this kind of reaction. So in that respect, it's catalytic in nature. So these kinds of things like copper and iron, et cetera, are called sensitizers right now. It's not particularly known whether they're having some kind of sensitizing effect or whether they're actually serving as catalysts and can be regenerated in the solution. Typically, transition metal ions are particularly effective for these reactions, and they include things to date: iron, copper, cobalt, nickel, and cadmium. And it's presumed that because they have these extensive D-shell configurations, they have varied redox properties, and certainly they have multiple oxidation states. It permits them to serve as centers for affecting various reactions amongst ligands in their outer and inner coordination spheres. And as I suggested here, possibly this methyl radical can come in and become a ligand here. So added sensitizers are effective not just for promoting reactions with halogens, but they may also enhance the production of reducing radicals. Charge transfer to solvent oxidation of metal complexes themselves yield aquo electrons in solution as reductants. These can rapidly react with H plus protons and generate H dot for further reduction reactions. And transition metal ions may serve as electron scavengers for conduction band electrons in heterogeneous systems where semiconductors are used. And this may enhance the oxidation and production of CO2 radicals. So here's an example. When we form carboxylate ligands of added transition metals, such as iron 3, plus, let's say this is acetate, we can form iron acetate. Ligand to metal charge transfer reactions in the 300 nanometer range take place, resulting in ligand to metal. The acetate ligand transfers an electron to the metal center, reducing it, forming a radical here, and that radical then becomes available for reaction in the solution. If this is acetate, of course, we get R dot. If it's formate, of course, we get H dot. Iron 2 and copper formed may also directly decrease OH in solution. They undergo reoxidation with the OH. And when this happens, just the presence of iron and copper may effectively remove oxidizing OH radicals from the solution and produce a more reducing medium. Then again, the iron and copper may be reduced all the way to nano iron and copper particles, or nascent iron and copper metal atoms of zero valence state, and they may set up electrochemical reduction sequences of their own with analyte ions of interest in the solution. So there's a lot of mechanisms that need to be investigated. One of the things recently done by Dan Hao in China is that he's applied what we call electron paramagnetic or electron spin resonance spectra to the investigation of what's happening with the direct detection of some of these postulated radicals in solution. And here we see in the case where there's 0% formic acid in the solution, looking at the ESR spectra, the only thing that's detected is OH. So there we have the oxidizing solution. Now, the moment that some formic acid is added to the solution in increasing amounts, we find increasing signals, ESR signals, from the carboxyl anion radical. And as they get high enough, the disappearance of the OH radical becomes quite evident. So clearly we're going from that oxidizing medium to the reducing medium. And here's a case where the carboxyl to hydroxyl ratio, taken from these peak heights here, is simply plotted in the presence of increasing concentrations of formic acid. And we find that it increases the ratio, so makes it more reducing. And there's something strange going on here that has yet to be deduced or delineated. The presence of both copper and cobalt produces some kind of synergistic enhancement in the reduction capabilities of this solution. A more recent article that is not really got a citation page number for it yet in Applied Spectroscopy Reviews. He's done some additional detection of now the methyl radical, and he shows the methyl radical can be formed in acetic acid. It's not present in formic acid, as you see here. Sorry, you don't see it there. That's formic acid and acetic. You see both of those radicals. And then the presence of cadmium and the presence of cobalt, the presence of mixture of cadmium and cobalt. So it's interesting reading, and it is final vindication that we do see these radicals in our photochemical reaction media. Dan has summarized in the literature, there's a number of sensitizers that has been used, and these are some of the enhancement factors that can be achieved with use of these sensitizers. Some of these enhancement factors I would take with a grain of salt, so to speak, with some of them are very large. Some of them are real, some of them are somewhat experimentally distorted because perhaps not optimum conditions were used for the generation of a particular analyte before the sensitizer was used. But nevertheless, Nickel, iron, cadmium, cobalt, copper, these are the ones that are typically used as sensitizers. So the practical impact of sensitizers is that they provide enhanced yields for the photochemical reaction. You can speed up the shorter irradiation times because of the enhanced kinetics. Obviously, it means there's an alter reaction mechanism, and the question is why? And clearly, in some cases, it may be involved with a change in the required wavelength. And this opens up the whole area of study of what is the impact of actual wavelength in these reaction mechanisms. We really don't know. I'll come back to that finally in a moment later. Just to give you a balanced perspective of PVG, interferences. There are some typical transition metal interferences, but they are a lot less than what occurs with classical chemical hydride generation using tetrahydroborate. There are interferences that can arise because of what we call shadow effects of other chromophores. For example, if you have a strongly colored solution, or that's in the visible, if you have a solution that is a strong chromophore in the ultraviolet, and it's present at orders of magnitude concentration higher than your analyte, it can absorb the incoming UV radiation, and therefore I0, the incident irradiation intensity that is important for the actual photochemical reaction you're interested in, is reduced. We'll call that a shadow effect. You may get enhancements in signals if you're trying to calibrate your system based on external calibration, because there may be unknown sensitizers in your real solution that you're giving that are producing elevated signals. And then again, probably most classically, there are radical termination interferences, and these arise from oxidants. So the shadowing, obscuration of relevant absorption bands associated with concomitants having higher absorption coefficients or higher concentrations. And one good example of that is nitrate and nitrite. They have very, very strong absorption bands in the deep UV, and those are present even at millimolar concentration levels. Secondly, as I mentioned in the previous slide, termination of radical chain reactions, and the most common example of that are oxidants. Dissolved oxygen, and not enough attention has been paid to dissolved oxygen concentrations in analytical solutions during PVG reactions, but certainly they can compromise the concentration of the carboxyl radical anion and H dot in solution used for a reduction of metal ions of interest. So these can soak them up and produce species that are no longer analytically useful. And then competitive complexation may give rise to additional intermediates with the analyte, which will have a different reactivity or absorption characteristics. So a study in real samples of organic complexing agents that may interfere with the system has not been undertaken to any great degree. One of the advantages, of course, of digesting solutions first with strong acids is that it often destroys all of these complexes. Finally, you can go into the literature where you can look up what happens with nitrate photochemistry. Extensive literature there. A huge amount of photochemical reactions, and many of them can be involved with our reduction radicals and cause problems for us. Here's an example of oxidant effects, again with the bromine system. Millimolar concentrations of nitrate and even lower millimolar concentrations of nitrite can cause some significant problems with photochemical vapor generation of bromine and bromide. So the impact of nitrate is very severe here, and it requires either the method of additions to obviate it or the need to get rid of the nitrate in the sample, or the need to try to prepare samples without adding nitrate to them. And there's been a number of investigations to try all of those different procedures. So as a final summary, all of the classical chemical vapor generation techniques that we use are amenable to photochemical vapor generation. So all of those semi-metals such as arsenic and tellurium and antimony, etc. However, in addition to that, I think we've demonstrated expanded elemental coverage, moving into the transition in noble metals as well as the non-metals, such as the chlorides. It's very green chemistry, utilizing stable, inexpensive reagents. It's a simple system. There's only one conduit manifold that you need. You're not blending reagents together with the sample. They can be prepared ahead of time as stable solutions for analyses. Obviously, we have enhanced analyte introduction efficiencies, which give rise to enhanced LODs for atomic spectroscopy detection. Lastly, we believe that these are radical-mediated reduction mechanisms that are responsible, due to the photogenerated redox capabilities of this particular suite of radicals, that speciation effects attributable to kinetics of reduction can be taken advantage of for measuring such things as selenate and selenite separately by PVG. And there's a necessity for looking at alternative wavelengths to explore that and exploit that, perhaps in conjunction with sensitizers and catalysts in these systems, because we have done PVG basically with all of the radiation from these low pressure lamps coming out and not paid any attention at all to specific wavelengths. For those of you who are more interested in PVG in general, there's probably almost 24 reviews of this subject area, and I've shown them here in increasing time frame, I guess. So even in 2017, 2019, and 2019, we're still getting reviews even in 2020 and in 2021. So it's still something where there's some research going on. PVG, I might mention, has many parallels with plasma, sono, and thermochemical vapor generation approaches, and these need to be further explored. I want to thank you very much for your attention.